squid and an eel and a shark in the hole in the bottom of the sea? Who hid from the eel and the shark in the hole in the bottom of the sea? There's a hole, there's a hole, there's a hole.
This first video is going to be pretty dense with new definitions, but these definitions are just analogs for R modules of things that we've already talked about quite a lot for groups and for ideals. Let's say that R is a ring with identity 1 not equal to 0. And like Dummett and Foote use this convention throughout when I write module, what I mean is left module. So when R is commutative, which it is most of the time in my mind for applications and the situations I'm most interested in, when I just say module, I'll mean left module. But when R is commutative, there's no distinction between module and left module. OK, so in the last lecture, to talk about the isomorphism theorems for modules, we needed to define the sum of two submodules of an R module M. So the first thing we'll do is just carry that over to the sum of a bunch of R modules. So let's say M is an R module, N1 up through Nn are submodules of M. The sum, written N1 plus N2 plus Nn, is the set of all things that can be written as A1 plus A2 plus An, where each AI is in Ni. So what are we doing? We're just taking sums of module elements from our set of submodules. You add two things in these submodules, you get another thing that's still in M. So what is this? This is going to be a subset of M. And in fact, it's not very hard to see that it's not just a subset, but it's actually another submodule. OK, so let's say that A is any subset of M. We'll define RA will be the set of all things that can be written as R1 times A1 plus Rm times Am, where, OK, I'm saying times now, but this is an element of the ring acting on an element of this R module M, where R1 through Rm, these are elements of the ring, A1 up through Am, these are elements of A, and M is some positive integer. All right, so one thing that this is emphasizing is that even if A is an infinite subset of M, we're just looking at things that are finite sums of these R linear combinations of elements of M. So sums of things that are Ri times Ai, where R comes from the ring and A comes from the set. So here's a convention. If A is the empty set, then we're looking at a sum of no things. And the convention is to say that Ra is just equal to the 0 element. All right, so in the case that A is a finite set, A1 up through An, we write RA1 plus Ran for Ra. And you can see why this is reasonable notation in this case where you have exactly these n elements. This Ra is called the submodule of M generated by A. This is very, very similar to the subgroup of a group generated by a subset, or the ideal in a ring generated by a subset. And OK, I already said something about this before. You can use the submodule criterion to check that Ra really is a submodule of M. And you should do that. You should check that once. You can also see pretty easily that it is the smallest submodule of M containing A, in the sense that any other submodule containing A also contains Ra. All right, so I made a little note here. This is underlined, containing A. So these definitions that we've given don't actually require that R has an identity. But this statement does. Right? The definition of Ra doesn't require that R contains a 1. You could still, in a ring that doesn't contain a 1, look at this Ra, this submodule of M generated by A. But without a 1 in R, it's no longer clear that A should be a subset of Ra. So we're using the fact that R contains a 1 to see that A really is a subset of Ra. So if you want to think of Ra being the smallest submodule of M containing A, you really need your ring to have an identity. All right, so now I said that the sum of a bunch of submodules is a submodule. If N1 up through Nn are submodules of M, this sum, N1 plus Nn, is the submodule of M generated by the union of all of these elements. So one important thing to note is that addition is commutative. But once you believe that that's true, then if you believe that the submodule generated by a set really is a submodule of M, then it's clear that the sum of a bunch of submodules of M is also a submodule of M. All right, so in this case, we have the union of all of these elements. You can check that this is the smallest submodule of M containing each one of n1, n2 up through nn. That any submodule containing all of these also contains their sum. That should be clear because a submodule is an abelian group under addition. So if you contain all the elements of n1 and n2 up through nn, you also contain all the elements in this sum. All right, so now we'll just establish a little bit of language here. If a submodule n of M, including possibly the case where n is equal to M itself, so you have the submodule n of M, and you have n equals Ra for some subset A of M. Then that subset A gets a name. We say that A is a set of generators or a generating set for n. Okay, so if n equals Ra, then A is a set of generators or a generating set for n. And we say that n is generated by A, and is generated by this subset. So we can now give a definition that's analogous to one we've seen for groups and for ideals. A submodule n of M, possibly including the case where n equals M itself, is finitely generated if there exists a finite subset A of M with Ra equals n. So what does that mean? A submodule is finitely generated if it has a finite set of generators or if it's generated by a finite subset. So I'll pause and erase. We'll go through a few more basic definitions that should feel very similar to things we've talked about for groups and for ideals. And then the bulk of this lecture will be about examples. When we talked about groups, there was a certain kind of subgroup that got a special name, one generated by one element, the cyclic subgroups. And when we talked about ideals, there were certain kinds of ideals that got special names, the principal ideals, the ones generated by one element. So what is the corresponding thing for submodules? A submodule n of M, possibly including the case where n equals M, is called cyclic if there exists an element A in M such that n equals R times A. What does that mean? That means n is generated by one element, that n equals Ra, that it is the set of all things that are of the form R times A, where R is in the ring. Okay, so the analog for cyclic groups and principal ideals here is cyclic submodules. And we'll see some examples coming up. So let me say a little more about submodules and generating sets. So one submodule n of M can have many, many different generating sets. One thing to note is that it always has at least one. So n, the subset n of M, is a generating set for n. That you can check that because n is a submodule, if you take R times n, you really are just getting back n. All right, so if n is finitely generated, then there exists a smallest generating set, right? So there's only, so n can be generated by finitely many elements. There's some smallest non-negative integer so that n is generated by a set of d elements, but n is not generated by a set of a smaller number of elements. Okay, so a generating set of this minimal size gets a name. It's called a minimal set of generators for n. So I'll come back to that, I think, in the next lecture and talk about some potential confusion with this terminology. Let me point out first that such a set is not unique in general, that you might have lots of different generating sets, even of this minimal size. All right, so if n is not finitely generated, it doesn't have to have a minimal generating set. If you think about it, any generating set has infinite size, and now we get into some kind of like delicate questions about the smallest subset or the smallest infinite set that generates n. And I would like to steer clear of that kind of issue for now. All right, so what I want to do for the rest of this video is talk about how these definitions that all come from Dummett and Foote are presented in a close but not exactly the same way in Conrad's notes, introductory notes on modules. So I like these notes quite a lot, and I would definitely recommend that you read both section 10.3 of Dummett and Foote and these notes of Conrad. So this comes from definitions 2.1 and 2.3 in Conrad's notes. I'm going to shift over to that reference for a little bit. So if M is an R module, an R linear combination of elements A1 up through AN of M is just an expression of the form R1 times A1 plus 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 Rn times AN, where, okay, this times, remember, is the action of the ring elements on your module elements. The collection of all of these R linear combinations is Ra, where A is your set of elements from A1 up through AN. So Dummett and Foote say, after giving all these definitions, that one of the best ways for understanding collections of submodules is to take these R linear combinations of elements. But they don't actually say R linear combination until after all of this has been discussed. Conrad opens up by telling you what an R linear combination is, and yeah, and then you can see how this matches up with this notion of taking the submodule of M generated by A. So this is the same thing with very slightly different presentation. What I like about the presentation in Conrad is that the way that this material about modules is presented makes a lot of comparisons to how things are presented in a subject you already know, linear algebra. So this should be familiar from linear algebra. If you take V to be a vector space over a field F, and you take a bunch of vectors, V1 up through Vn, in your vector space, the span of V1 up through Vn is the set of all linear combinations of these vectors where your coefficients live in your field. You're a vector space over some field, your coefficients live over that field. So it's just a collection of all the alpha 1 times V1 plus 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 alpha n times Vn, where this times is the scalar multiplication of your field on your vectors. Okay, so I'll pause and erase and say a little bit more about this. We've talked about R linear combinations and recalled the notion of the span of a set of vectors. A spanning set of an R module M is a subset, a collection of AIs that all live in M, such that every element X in M is a finite R linear combination of these AIs. That is, every X in M can be written as a sum over this index set I of Ri times AI, where these Ri's all come from the ring, and Ri is 0 for all but finitely many of these I. That is, our subset, our spanning set, can be infinite, but when we take our linear combinations, all but finitely many coefficients have to be 0. This notion of a spanning set matches up exactly with what we said earlier about what it means for a subset to be a generating set for a submodule n of an R module M. What I like about the presentation here is that this makes it clearer what are we doing to generate these submodules. We're just taking collections of R linear combinations of elements in our subset, and this looks just like what happens when you take the span of a bunch of vectors in a vector space.